Hello students, welcome to our YouTube channel Experience Tutor. Today we'll discuss class 12th physics, moving charges and magnetism. Chapter 4, NCERT solution, part 1. Our mission is to provide free classes on YouTube for all the students of class 6 to class 12 and also for the students who are preparing for IIT, JEE, NEET, NDA and other competitive examinations. Before we start, we have a humble request. Please subscribe, like and share our channel among your friends and relatives. Please click on the subscribe button to support us and also click on the bell icon to get automatic notification whenever a new video is uploaded by us. Let us begin today's class. So the first question is question number 4.1. A circular coil of wire consisting of 100 turns, each of radius 8 centimeter, carries a current of 0.4 ampere. What is the magnitude of the magnetic field B at the center of the coil? Let us see the solution. So the solution for 4.1 is number of turns on a circular coil n is equal to 100, which is given in the question. Radius of each turn r is equal to 8 centimeter, which is equal to 0.08 meter. Current flowing in the coil I is equal to zero point 0.4 ampere. Magnitude of the magnetic field at the center of the coil is given by the relation. We have to remember this formula. B is equal to mu naught by 4 pi 2 pi NL upon R, where mu naught is equal to permeability of free space, which is equal to 4 pi multiplied by 10 to the power minus 7 T m per ampere. So this is a constant. Putting the value of mu, n, l and r, we will get the following: 2 pi into 10 to the power minus 7 by 4 pi into 2 pi into 100 into zero point 0.4 upon 0.08. Upon solving, we get 3.14 multiplied by 10 to the power minus 4 t. Hence, the magnitude of the magnetic field is 3.14 into 10 to the power minus 4 t. So this was a directly formula based question. First, write the structure, whatever is given in the question, and put the value into the formula. So these are one of the easiest sums in physics which are directly formula based. Let us move to the next sum. So let us now see the next problem, that is 4.2. Now, a long straight wire carries a current of 35 ampere. What is the magnitude of the field B at a point 20 centimeter from the wire? Let us see the solution. So, current in the wire I is equal to 35 ampere. It is already given in the question. Distance of a point from the wire r is equal to 20 centimeter is equal to zero point 0.2 meter is also given in the question. Magnitude of the magnetic field at this point is given as modulus of B mu naught by 4 pi 2L upon R, where mu is equal to permittivity of free space, its value is 4 pi multiplied by 10 to the power minus 7 Tm A inverse. Now putting the values, we get modulus of B is equal to 4 pi multiplied by 10 to the power minus 7 upon 4 pi multiplied by 2 multiplied by 35 upon zero point 0.2, which is equal to 3.5 into 10 to the power minus 5 t. Hence the magnitude of the magnetic field at a point 20 centimeter from the wire is 3.5 multiplied by 10 to the power minus 5 t. Let us see the next question. So the next question is 4.3. A long straight wire in the horizontal plane carries a current of 50 ampere in north to south direction. Give the magnitude and direction of B at a point 2.5 meter east of the wire. Let us see the solution. So current in the wire I is equal to 50 ampere, which is given in the question. A point is 2.5 meter away from the east of the wire. This is also given. Therefore, magnitude of the distance of the point from the wire r is equal to 2.5 meter. Magnitude of the magnetic field at the point is given by the relation B modulus of B is equal to mu naught by 4 pi 2L upon R, where mu naught is the permittivity of free space. Its value is 4 pi multiplied by 10 to the power minus 7 Tm A inverse. So putting the values, we get 4 pi modulus of B is equal to 4 pi 10 to the power 7 upon 4 pi multiplied by 2 multiplied by 50 upon 2.5. Upon solving, we get 4 into 10 to the power minus 6 t. The point is located normal to the wire length at a distance of 2.5 meter. The direction of the current in the wire is vertically downward. Hence, according to the Maxwell's right-hand thumb rule, the direction of the magnetic field at a given point is vertically upward. Let us move to the next question. Now, let us see the exercise problem number 4.4. A horizontal overhead power line carries a current of 90 ampere in east to west direction. What is the magnitude and direction of the magnetic field due to the current 1.5 meter below the line? Let us see the solution. So the solution is for 4.4 is current in the power line I is equal to 90 ampere. Point is located below the power line at a distance r is equal to 1.5 meter. Hence, magnetic field at that point is given by the relation modulus of B is equal to mu naught by 4 pi 2r 2L upon r, where mu naught is the permittivity of free space. Its value is 4 pi multiplied by 10 to the power minus 7 Tm A inverse. Putting the values, we get modulus of B is equal to 4 pi multiplied by 10 to the power minus 7 upon 4 pi into 2 into 90 upon 1.5. Upon solving, we get 1.2 multiplied by 10 to the power minus 5 t. The current is flowing from east to west. The point is below the power line. Hence, according to Maxwell's right-hand thumb rule, the direction of the magnetic field is towards the south. Let us see the next problem. Now, let us see the problem number 4.5. What is the magnitude of magnetic force per unit length on a wire carrying a current of 8 ampere and making an angle of 30° with the direction of the uniform magnetic field of 0.15 T? Let us see the solution. So current in the wire, which is given in the question, I is equal to 8 ampere. Magnitude of the uniform magnetic field B is equal to 0.15 T. Angle between the wire and the magnetic field theta is equal to 30°. Magnetic field per unit length on the wire is given as F is equal to Bi sine theta. Putting the value, we get 0.15 multiplied by 8 multiplied by 1 multiplied by sine theta. Upon solving, we get zero point 0.6 Newton per meter. Hence, the magnetic force per unit length on the wire is zero point 0.6 Newton per meter. Let us see the next problem. Now we'll see problem number 4.6. A 3 centimeter wire carrying a current of 10 ampere is placed inside a solenoid perpendicular to its axis. The magnetic field inside the solenoid is given to be 0.27 T. What is the magnetic force on the wire? Length of the wire L is equal to 3 centimeter, that is 0.03 meter. Current flowing in the wire I is equal to 10 ampere. Magnetic field B is equal to 0.27 T. Angle between the current and the magnetic field theta is equal to 90°. The magnetic force exerted on the wire is given by F is equal to BIL sine theta. Putting the values, we get 0.27 multiplied by 10 multiplied by 0.03 sine 90°. Upon solving, we get 8.1 multiplied by 10 to the power minus 2. Hence, the magnetic force on the wire is 8.1 multiplied by 10 to the power minus 2 Newton. The direction of the force can be obtained from Fleming's left hand rule. Let us see the next problem. Now let us solve the problem number 4.7. Two long and parallel straight wires A and B carrying current of 8 ampere and 5 ampere in the same direction are separated by a distance of 4 centimeter. Estimate the force on a 10 centimeter section of wire A. Let us see the solution. So, the current flowing in wire A, IA is equal to 8 ampere. The current flowing in wire B, IB is equal to 5 ampere. Distance between the two wire R is equal to 4 centimeter, that is 0.04 meter. Length of the section of a wire A, L is equal to 10 centimeter, that is 0.1 meter. Force exerted on the length L due to the magnetic field is given by F is equal to mu naught IA IB L upon 2 pi r, where mu naught is equal to permittivity of free space, that is 4 pi multiplied by 10 to the power minus 7 Tm A inverse. Force is equal to 4 pi multiplied by 10 to the power minus 7 multiplied by 8 multiplied by 5 multiplied by zero point 0.1 upon 2 pi multiplied by 0.04, which is equal to 2 multiplied by 10 to the power minus 5 n. The magnitude of the force is 2 multiplied by 10 to the power minus 5 n. This is an attractive force normal to A towards B because the direction of the current is the wires in the same. Let us see the next problem. So now let us solve problem number 4.8. A closed wound solenoid 80 centimeter long has 5 layers of windings of 400 turns each. The diameter of the solenoid is 1.8 centimeter. If the current carried is 8 ampere, estimate the magnitude of B inside the solenoid near its center. Let us see the solution. So, length of the solenoid L is equal to 80 centimeter, which is equal to zero point 0.8 meter. There are 5 layers of windings of 400 turns each on the solenoid. Total number of turns on the solenoid N is equal to 5 into 400, that is 2000. Diameter of the solenoid is equal to 1.8 centimeter, that is 0.018 meter. Current carries by the solenoid I is equal to 8 ampere. Magnitude of the magnetic field inside the solenoid near the center is given by the relation B is equal to mu naught Ni upon L, where mu naught is equal to permittivity of the free space, that is 4 pi multiplied by 10 to the power minus 7 Tm A inverse. B is equal to 4 pi multiplied by 10 to the power minus 7 multiplied by 2000 multiplied by 8 upon zero point 0.8. Upon solving, we get 2.5 multiplied by 10 to the power minus 2 T. Hence, the magnitude of the magnetic field inside the solenoid near its center is 2.512 multiplied by 10 to the power minus 2 t. Let us move to the next question. Now let us solve question number 4.9. A square coil of side 10 cm consists of 20 turns and carries a current of 12 ampere. The coil is suspended vertically and the normal to the plane of the coil makes an angle 30° with the direction of a uniform horizontal magnetic field of magnitude 0.8 T. What is the magnitude of the torque experienced by the coil? Let us see the solution. So, length of the side of the square coil L is equal to 10 centimeter, which is zero point 0.1 meter. Current flowing in the coil I is equal to 12 ampere. Number of turns on the coil N is equal to 20. Angle made by the plane of the coil with magnetic field theta is equal to 30°. Strength of the magnetic field B is equal to 0.8 T. Magnitude of the magnetic torque experienced by the coil in the magnetic field is given by the relation tau is equal to NBIA sine theta, where A is equal to area of the square coil, that is 1 into 1, that is zero point 0.1 into zero point 0.1, that is meter square, that is zero point 0.01 meter square. So tau is equal to, putting all the values, we get 20 multiplied by 0.8 multiplied by 12 multiplied by 0.01 multiplied by sine 30°. Upon solving, we get 0.96 Newton meter. Hence, the magnitude of the torque experienced by the coil is 0.96 Newton meter. And this is the end of today's chapter, today's class. Before we close, we have again a humble request to you. Please subscribe, like and share our channel among your friends and relatives. Please click on the subscribe button to support us and also click on the bell icon to get automatic notification whenever a new video is uploaded by us. Thank you for watching our videos and supporting us.